Hello everyone, I'm Brian, and I was the person who wrote the MAME core for the Naboo PC after it came out. So this will be a talk about the basic architecture of the PC and using some source code examples how I implement it in MAME. So this is, for anyone who hasn't seen it, what a complete Naboo system looks like. The bottom box is the main PC, and it was released in about 82, I think, and by a Canadian company. It's a PC being basically a Z80 processor with a TMS 9918 video chip and an AY8910 sound generator. But the thing that really made this unique for its time was the top box there, which is the home computer cable adapter, which allowed it to download and load its software over your local cable network. It could do that at fairly high speeds at around 6.3 megabits, I think, though it was somewhat limited because it actually transferred that to the computer over an RS-422 connection that only ran at 111.9K. This is a diagram of what the setup would look like. It would have a head-end computer at the cable office that would modulate the software cycle and then combine it with your standard TV programming, which would be picked up by the adapter and then transmitted to the actual PC. And the software was sent in a cycle, so instead of requesting a particular piece of software, all the software would be continuously transmitted in a cycle like that, and the adapter would just wait for the correct piece to come around and download it. So that could cause maybe 20 seconds or so of delay, depending on where you were in the cycle. These are just some photos of the current emulation. When the system booted up, you would have a main menu that gave several categories to choose from. And there's quite a wide variety of software. You had some standard games, Pac-Man, Qbert, many others, but you also had a couple languages that had a version of BASIC for it, as well as a version of Logo. And there's even some productivity software. There's a writer and a spreadsheet, both of which could save data to a floppy if you have the floppy expansion that was also available for the system. And the floppy could also boot a version of CP/M 3.0 that was released for it. So, like I said, the basic architecture is a Z80 processor, and this is how you would configure something in MAME. There's always a main configuration function where you define which components are there, and it's where you link up the callbacks for what happens when certain events happen. So you have a Z80 processor that runs at 3.58 megahertz. Then you have to define a raster screen object, and it's going to be attached to the TMS 9918, which in the Naboo is also equipped with its own video RAM. And the third main component is the AY8910, which runs at 1.79 megahertz, and that's the standard clock that's used for a lot of the other peripherals in the system. Now, to create a memory map in MAME, you're going to call the set address map on the CPU, and it can set address maps for various types of memory. In this case, we just want program memory, and we give it a function that looks something like this. The total memory available for the system was just a simple 64K block from 0 all the way up to 64K. This will define that block and assign it to an anonymous block of RAM that's automatically created in MAME for it to handle. The next thing I needed to do was implement the BIOS for the system. The BIOS there were both a 4K and an 8K version of the BIOS available. Most of the Naboos being shipped all have the 4K on the real hardware. It would there was a solder jumper that you would have to like manually desolder and resolder to change to the 8K. In MAME, I've basically just chosen to use the 8K ROM, and 4K is implemented simply by defining the 4K ROM, loading it from the disk, and then mirroring it in the upper 4K rather than actually having a switchable one. So you can use both ROMs. So here we define the 4K ROM and then mirror it. And here we define the 8K ROM. And the main difference between these two were that the 8K ROM supported floppy booting, whereas the 4K just booted off network. There are actually several other ROMs that are supported that were given to us by Leo from dumping some of his development machines, and those are supported in the actual MAME, but for this, we have just the original two ROMs that we had available. To actually implement the ROM sits at the bottom 8K or 4K of memory, and in the real hardware, it can be disabled via a control register, and also if you write to that 8K, it writes to the underlying RAM rather than nothing. The ROM actually uses this because when the machine first boots, it will copy itself to the low 8K of system memory and then disable itself, completely running the rest of its code directly from RAM. And in MAME, we can take care of this with a view, which allows us to define a selectable submap. So this view will cover the bottom 8K of the RAM, and if it's disabled in MAME, it will not have any effect, and you'll just get reads and writes from the RAM. In the main reset function, you can say we're installing the ROM, which takes the size of the ROM and a pointer to where the ROM is and installs it in that view. So now if we try to write to that view, it'll go to the RAM, and if we try to read from it, it'll read from this view, and then we enable it so that on reset, the memory map looks correct. The next thing we want to do is quickly implement the basic I/O mapping. It works relatively similar to the way we did the program memory. We just use set address map to map a map function for I/O memory. And we're going to start off with the basic I/O that we have. Register 0 is the control register, which we will implement shortly. Register 40 and 41 are mapped to the sound chip, with 41 being the address latch for the sound chip, and address 40 being the data port. And finally, we have A0 and A1, which are mapped to the registers of the TMS 9918 read and write functions. And this is the mapping for the control register. At the moment, all we're going to be concerned about is bits 3 through 5, which control the state of the front panel LEDs, sans power, which is always on when it's powered. So that's what we're doing here. We're just reading the 3 through 5 bits and storing them in the LED array. And then finally, we need to look at the first bit and see if it's set. If it's set, we disable the ROM. And if it's not set, we enable the ROM again. And that's how the software will turn the ROM on and off. Next, we should implement the interrupts. And the system has a total of 8 interrupts. There's 2 for the transmit and receive for the HCCA port, 1 for the receive on the keyboard, 1 for the video blank, and each of the 4 expansion slots also have their own dedicated interrupt. Those interrupts get combined with the port A the IO port A register on the sound chip, which is used to turn on and off the interrupts. So this NAND gate here is combining the physical interrupt with its enable switch to make sure they're turned on before passing it to the interrupt priority encoder, which is going to take those interrupts and output the state of whether there is an interrupt on the in output, which is connected to the CPU, and its inverse on the E0, which is goes to port B telling you if there's an interrupt or not when it's set. And then A0 through A2 is the actual interrupt or IRQ number. This gets stored also in the sound IO port B, as well as being placed onto the bus whenever when the interrupt is acknowledged. The system itself uses IM mode 2, so it will take that low 8-bit value and combine it with the I register of the Z80 to form the actual vector for the interrupt. So here we have the basic configuration we need. We have to configure an acknowledge callback for the main CPU. The only interrupt we're currently handling is the VBlank interrupt. And then we define a read and write callback for the port B and port A so that we can handle those. And here are those functions. The port B, all it has to do is return the value that is currently stored in port B to the caller when you read from it. The write function for port A only needs to do anything if the value changes from what it was, but it'll store that it'll update the stored value, and then it has to update the interrupt state, which is what update IRQ does. The int W is the callback function we use for, whenever an interrupt is triggered to store its state. It is implemented in MAME as a template function because basically the only thing that changes is the bit number, so we can just implement a template function and have one implementation of it. And then the callback function is basically just masking out the interrupt number from port B and returning that value, which MAME will then put on its emulated data bus for the CPU to use. Update IRQ basically does what was in the diagram earlier. It's going to take the port A and get the NANDed value with the current interrupts that are active. We then pass that to the function that I have written there, which emulates a priority encoder, so the output bits are the same as what the priority encoder would output given its set of inputs. Bit swap is just rearranging those bits so they're in the right order and then setting them in the port B register. And finally, we're going to look at the output bit that tells state of the output bit and use that to set the interrupt line on the CPU, which will either trigger or clear an interrupt depending on what it is. The keyboard port is the next thing I chose to implement. It has an I-85, I-8251 as the UART controller for that. And it at lines 23 and 24, I believe, I'm defining the clock for the receive clock. The receive clock is running at 111.9 K, which gives us a baud rate, a slightly odd baud rate of 6,992 about for the actual keyboard. And then I define a virtual RS-232 port and have the default and only currently selection of the NABU high-level emulated keyboard. I have not emulated the actual low-level keyboard at the moment. I'm just emulating the serial protocol that a keyboard would send to the actual NABU. And then we have ports 90 and 91 get added to our I/O map. 91 is used for the status port of the UART, and 90 is the data port. And the keyboard device function is just a helper function that lists what devices are supported by the keyboard RS-232 port, and currently we only support the HLE keyboard that I wrote for it. So going over the basic protocol for the keyboard, like I said, it's a serial protocol. All ASCII are sent as is, so basically 0 through 7F hex are sent for each of the possible ASCII codes. Then there are several codes at 90 through 95, which the keyboard uses to report errors or conditions. As far as high-level emulation is concerned, the only one I really had to care about was the 94 one, which is the software watchdog. That is sent approximately 3.7 seconds, and if it's not sent, the NABU will give you a keyboard failure error when it boots up because it won't think there's no keyboard attached. The NABU has a bunch of special keys that start at key code E0 and go through EA. Those are things like the right-left arrows, page left, page right, special keys like sim and pause. Those keys are unique in that they're the only keys that also have a break code, so that's what the F0 through FA is. E0 would go when right arrow is pressed down. F0 is triggered when it's released. And the final set is there's values 80 through 83, which are prefix bytes because the keyboard also handles the 2 joystick ports. And these are prefix bytes for joysticks 1 through 4. There are only 2 joysticks, but there are also 2 unpopulated ports on the PCB. And the ROM actually sends codes for those, so presumably if they were populated, you could support 4 joysticks. This is the second byte that follows the prefix. It always has a header of 101, and then the last 5 bytes are basically which controls are set, so fire up, right, down, and left. And for example, if joystick 1 was pushed, had the fire pressed, it would send 80 followed by B0, and joystick 2 had up and left simultaneously pressed, it would be 81 and then A9. The last bit is for the main system is the HCCA. Well, there's one more after this. Okay, next we have the HCCA port, which was the RS422 port that had the adapter, a cable adapter attached to it. It does not use the standard 8251. It uses another chip, which is emulated. The chip I'm actually emulating here is not the same chip, but it's functionally equivalent. It behaves the same way and has the same pinout as the actual chip used on the NABU. But we're going to set the interrupts for the 2 transmit and receive lines. We're also setting a callback because we capture the framing error and overrun pins on this chip, which will be set as a couple bits in the port B register. And then the clock for both the, starting at line 37, the clock for both the transmit and receive lines is running at 1.79 megahertz. So that gives a baud rate of 111.9 kbaud about for the actual adapter, which is yet another slightly odd baud rate. And then we create the virtual RS-232 port for the system, and we give it a null modem by default. Null modem is useful because it's a special type of connection in MAME that allows you to do things like bit bang over, for instance, a TCP connection. So using this, we can set up a TCP connection and have an external adapter emulator that can provide that TCP connection for the emulation. And it uses port 80, just port 80 as its data port for reading and writing. And you can see the framing error stores its value in bit 5 of port B, and bit 6 is where the overrun error is stored. And then just HCCA devices defines just the null modem device for this port. And this is the actual last main port on the system. It's fairly simple. It's a standard Centronics style printer port. We just define an output latch to store the data data byte that we're trying to print, and set that to be the output latch used by the Centronics port, and also set a handler to support reading the busy bit from the Centronics port so that devices attached can inform the computer that they are busy. This uses just B0 for writing. There's no read port for this. that will just write that data to the output latch. The one other thing, we're going to have to update our control register, and it uses bit 2 in the control register for the strobe port. So changing that, I think it's low to high, will cause anything attached to the Centronics port to determine that there's data to be read, and it'll read whatever's in the latch. And then the busy bit sets port B bit 4, which can be read by like software to determine whether the printer is busy or whether it can accept new data. So at this point in the thing, I had basically a fully emulated system, but I wasn't content to stop there. I wanted to actually add support for the various expansion cards. So these are just some photos of some of the original cards. This was the floppy controller. It also had an RS-232 card for it. And the final of the 3 expansion cards that we knew of was the hard drive controller, which is technically the simplest of the cards as far as hardware is concerned, but that's because all of the real work used a WD-1000 series controller to drive the MFM hard drive, and this was just a set of buffers and address decoders in order to send the right data to the WD-1000 and read the data back. So the expansion bus here has 4 slots to it. Each slot is given its own interrupt, which you can see there starting at line 50. And then the 4 actual slots are defined starting at line 54. There's the null pointer at the end, just means we don't, by default, load anything into those slots. They're empty unless you specify what you want to put in them. Each slot had 16 I/O ports assigned to it. The addresses on the bus slot was basically only 4 bits long, so there's a total of 16 addresses, and then a chip enable line that would be set when that slot was selected. So here we're just going in and adding read and write functions for each slot to those addresses. Expansion cards would have an ID assigned to them that would be read from reading the 16th I/O port on that card, and the OS uses that to scan the entire expansion bus and determine which, if any, cards are selected there, so they know if it has an RS-232 or a floppy controller or a hard drive controller, etc. Floppy drives are fairly simple. They have a 1797, 2 floppy controllers, runs at about 1 megabyte or megahertz, sorry, and uses a pair of 5.25 double density drives. The read function is equally fairly simple. It's just got the first 4 ports are mapped into the floppy controller, and the final port just returns the ID of 10 hex. The write is also relatively simple. First 4 ports, again, to the floppy, and while most of the cards don't have a write to port F, the floppy drive does. And it's used to basically select which floppy is active. So bits 1 and 2 select which drive is set, and if either of them is set, we actually enable the emulated floppy motor as well. Bit 0 selects the density, so you could do single density or double density. One interesting thing here is the fact that the floppies actually encode what type of media they are, whether they're like single-sided double density, double-sided double density, or double-sided quad density. And they do this by writing that data in out-of-band MFM data. They do it in encode this when they're formatted in track 0's index gap. Took us quite a while to actually figure out why our dumped floppies were not working on real hardware or the emulator. This shows basically that they each have a header, then there's 4 bytes that I think is the volume ID. They don't seem to be used for anything. Following a byte that tells the actual type which is basically whether it's 40 track, single-sided, 40 track double-sided, or 80 track double-sided. And then the following set of bytes is basically a CPM disk parameter block that gives stuff like sectors per track, number of the bytes per physical sector of the disk, how many directory entries, etc. The RS-232 controller looks kind of like this. It uses a 8251 and a 8253. The 8253 uses two of its outputs to generate the baud rate timers for the 8251. And whenever there's a byte ready, the RX ready line is attached to the interrupt of this card. Again, this is the read. You've got the 8251 is ports 0 and 1, and then 4, 5, and 7 control like loading the timer data into the timer and configuring the timer. And port F on read is its particular ID. Write is similar, except this time there is no write to the port F. Port F is read only on this card. Hard drive controller, like I said, is even simpler. We just define a WD1000 object and attach that to a hard drive. And again, read is just all 8 of the 0 through 7 of the first 8 ports, and port F for the ID. Write is just the first 7 ports. The actual protocol for this is very, very similar to IDE, but not quite. And because we don't have any official hard drive image dumps from Leo's NABU at the moment, I ended up writing some boot code that allows MAME to boot from the actual hard drive. So there's no real world example of it doing this on current hardware, but MAME can actually boot from hard drive images that have been created for the system at the moment. This is the serial protocol. Most of this was originally figured out by DJ Sures, but the adapter will first, or the NABU will first send a hello message to the adapter, which if you don't reply, you'll get an error about adapter failed. But it should reply with an ACK and confirm set. It then asks for the status, and after every command, you get an ACK back from the adapter. And the status it's asking for is the channel status. It basically wants to know whether it has a channel lock for the channel it expects the data to be on. And you reply with a 1F if you do. Otherwise, you reply with a 9F, in which case there's another command 85 that requests you to send it the channel ID. Then you do the set status, ACK, set the loading status, which is a fixed pair of bytes. And then the next you're doing a packet request. Packet request for each packet always sends the packet number of the segment, because there's segments, which is an entire file you're requesting, and then that's divided up into about 1K packets. So this will ask for the packet number and which segment it's from, and you should return a 90 E4 or 91 E4 if it's authorized. 90 E4 will tell it it's not authorized. Most current adapters we have basically just use 94. If the file doesn't exist on disk somewhere, it'll return a 90. In this case, the actual computer will send the ACK of 1006, and then the adapter needs to send all of the packet data, which includes the header and the actual data, and it will end with 10 E1. This means, however, that any value of 10 hex in the packet data has to be escaped. So you will, anytime you see a 10x in the packet data, the adapter has to send them twice, so it'll escape that data. And it'll keep doing the request for packet number until all the packets of a segment have been sent. This is the serial packets, what the header looks like. You've got the segment ID, the packet number, the owner and tier, which I'm not 100% what they're used for. We always send the same thing. I believe they were used for authorization because like you might subscribe to different tiers on the original system. Couple mystery bytes, which as far as I can tell, no one knows what they're for. The type is kind of important because that is set for various things, and I think bit 4 tells it, bit 4 being set tells it that it's the end of packet, and that's how the computer will know that you're done sending packets and it doesn't need to request the next one. The offset is the offset in the file that this packet starts at, so it can reconstruct them in the same order in memory. And then the data consists of however much data is being sent up to 991 bytes plus a CRC16 checksum, 2-byte CRC16 checksum. I have implemented a basic for the original protocol emulator inside of MAME. So if you just want to use like the original basic protocol, there have been at least 2 other extended protocols that aren't supported in MAME at the moment that people have written. But the basic original protocol is emulated in MAME for both like locally stored code as well as code that's off of the NABU.ca site, downloaded and run automatically. And this would be what the state machine looks like. We've got the idle state, channel request, segment request, set status, get status, and send request. And for each, here's what we do when we're in the idle state. We're going to check to see which of the command bytes we have, respond with like the necessary response bytes, and update the state to the next one, state if necessary. Set status, we basically just transmit E4. So set status, we're reading in 2 bytes following this, so that's why we wait for mstate to be 1. Mstate counts how many bytes, how long we've been in this state. We don't store those because we don't actually care about what they're sending. But after the second byte, we'll transmit the E4 byte and return to idle. Get status, we actually do care, so we're going to look at the first byte and then check and then transmit either 9F or 1F, depending on whether the MAME has been configured to ask for a channel or not. And then after that, we'll send the 10 E1 and return to idle. Channel request, very similar. This is if you send like 9F instead of 1F, it will do this, and it's going to get and store the channel in the next 2 bytes. Segment request is very similar still. It has it has 4 sets of stages where it's going to read the packet number and then 3 bytes for the segment, combine them. The load segment is going to take the combined segment number and load the segment from disk. This one is one based off of the local loading, so it doesn't support remote loading. But that will load it from disk and update to send segment and store the segment ID in the class. And transmit the authorized byte. If it couldn't find the segment, the else will transmit the unauthorized saying you don't have access to this or that it's not found. And then the send segment is a bit odd because it gets ready to send stuff, but we can't just like send, so like the first it calls parse segment. This is going to take the segment you loaded from disk into memory and chop it up and create the necessary headers in it to it and store that as a vector so that we can send each packet of it at a time. The main issue is that we can't just like drop those all out at the emulated serial port, otherwise we overrun it and end up losing all of our data and stuff doesn't work. So what I do is I start a timer that ticks every certain number of hertz, which I just kind of found by like trying. so that it will go not terribly slowly, but not too fast that it drops stuff. And this timer is where the bytes actually get sent. That's the second function down there. It's going to send the current byte we're on. If the current byte is 10 hex, it'll send a copy of it before sending the normal copy so that we can escape it. And when that function gets, when the offset that we're sending gets to the length of the file, then we set ourselves back to idle and send the confirmation bytes that we're finished. So that's most of what I have. This is just a list of the current internet adapters that are out there. There's the original one by DJ Suarez. He's the one who first did that, and it works fairly well. You've also got a couple others. There's the NABU Network Emulator by Nick Daniels at his GitHub account there, which is another perfectly good one. I like that one because it exposes a web interface for configuring which files it's going to send when you connect to it. So it makes it very easy for me to like set it up on one system and then configure it elsewhere. I use it on my Pi, so I can have my Pi just sitting there handling the code and then configure it from my laptop or something. Naboo D is a completely command line driven one that Jason Thorpe wrote. It's also pretty nice. I've used it a bunch and played around with it. And then there's Naboo Server with Geek with Social Skills, or Sean wrote. And that one, last I checked, is only available for like Windows, but he's planning to release the source once he gets things stable and working. And then there's emulation. So there's MAME, which you can download the official MAME source at the moment, and I've got most of my changes ported over. There's like two major ones that I haven't actually ported in there. The latest code is available at my branch, which is where I did all the original work before pulling out bits and pieces and sending them one at a time over to MAME to get approved and fixed up and into the thing. And then there's also Marduk, which is another person on the Discord server that has been writing this emulator. And it's, unlike MAME, it's completely standalone, so it's a lot smaller. It also is less concerned about accuracy of hardware emulation versus does this actually work and do what it's supposed to. But I've used it some. It's pretty good system. One thing is like there's someone who's ported it to the PSP and PSP Vita, as well as I think there's an like built into it. There's an in progress, but still doesn't quite work DOS version of it as well. And then just a bunch of things like James Pellegrini. Without him, we would not have a bunch of Nabus available on eBay for people to buy. Adrian Black. I would not have bought a Nabu if I hadn't watched his video. Leo is the one who gave us all the software. So we would not have the official software and cycles without him. And DJ Suarez basically reverse engineered the protocol and has done a lot to get a lot of software out there and code working with the Nabu. And basically everyone else on the Discord channel that has contributed anything at all. So, and that's about it. And I guess I went a bit quicker than I thought, but so any questions at all?
Any of Leo's original gaming software out there? What's happened to the actual games themselves?
What?
The actual games, like his Pac-Man?
Yeah, they're out there. Let me see if I can actually, since we have time.
Game executables are there, but I'm looking for like
The source code?
source code to see how How do you program those techniques?
Yeah, the games out there. Leo has a bunch of the software, and I'm not sure he's gotten around to releasing it yet. But he's like going through his disks to like get anything he can off, and is planning to release the software. Any others?
I'll give you another one. So a bunch of us have these NABU, the $79, or we got it for
Yeah.
20 when they were 20. What can you do with it now? What do you need to actually emulate and connect to the internet?
So basically, like right now, if you have like the original hardware, you need a USB to RS-422 adapter, which there's one popular one that basically DJ recommended, and I think most people have went and bought. It's just on Amazon. It's a DTEC adapter. Outside of that, you need to create a cable that has like a DIN 5 on one end and a standard 9-pin on the other. There are some people online that have made some pre-created ones that you can purchase. I ended up just soldering that myself and remembered why I hate soldering DIN sockets.
That's it.
Yeah.
Great.
Yeah, I might be able to demonstrate a little bit of the actual running emulator here if I have some extra time, which it looks like I think I do.
The documents you use?
Yeah, so like that's the other thing. Like I did this before I even had like the NABU in my hands. And there's two things for that. One, that I was using MAME, which basically has most of the core components already emulated, and it becomes a matter of like understanding how they work together and how to hook stuff up. But the second is, again, James has released a technical document that has like basically the entire keyboard protocol in it that I went over, like all of the I/O ports, what the bits do, full schematics basically of the system. So I was working with that plus like the MAME framework to be able to like fairly easily figure out how stuff worked. Let me see if I can get one. Let me actually move this over here. Okay, that's annoying. I'm trying to see if I can get this to actually show up on that screen. Let me bring this over here where I can see again. There we go. So it should post. Again, I guess we're not going to have sound for this, but sounds less important. This is what it'll do when it starts to load. Normally, if you had sound, there would be a progressing increase of like notes, which you could use to tell that it was actually like receiving data. Being a bit slow.
Are you using the network that doesn't work so well?
Oh, well, you know, maybe that's it. I don't know. Yes. So you get like this little screenshot of Starfield. And then the NABU logo.
Just some sound.
Yeah, it's just coming out of my speaker though, so you can actually hear that. But then you have the different things here. So you've got network services. There's Pac-Man and Qbert. You got Moonsweeper, Amway, Penny Saver. And missing the keys. I'm not sure like the organization for some of these things, because I'm not sure like network services is where I would expect to find Pac-Man, Qbert, and Minesweeper, but and you'll find like some of the games like are in different places too. Like this has most all of the games, but you can find some programs cross organized. You've Galaxian, Miner 2048, Dig Dug, Quest for Tires, Time Pilot, Wing War. All right. There is, I don't know, let's like look up Family Fun. So there's a submenu here, video games, which has different video games. You've got Ping, which is a fairly obvious clone of Pong. Tank Commander, Zipper, Renegade. Where, I think, what's in education? Language arts. That's where you find basic and logo are in there. Hand-eye, logic, strategy. I don't know what's in strategies. Oh, this has got backgammon, checkers. And what did I check out? So most of these are like basically, not all of the software is here, some of it will fail to load. Let me see if this one loads. No, that one crashes.
Have you tried joysticks on it?
Joysticks do work. I have some with me. I can demonstrate it later, but yeah, joysticks will work if you like plug in a USB. By default, it has. Let me actually just restart it. Show you. And again, it seems to not. Oh, that's because I hit the wrong key. That would explain it. Insert tab. So if you go to input settings, you can sign. The default is to use like the number pad for joystick 1, because those aren't used anywhere else. And then joystick 2 is not assigned. But if you have like a USB controlled joystick, you can plug it in here and assign it to whatever buttons you want. I have a couple of USB NES controllers or whatever that I've used with this, just assign one of the buttons to fire and the D-pad to the direction keys, and it works fine. So yeah, that's pretty much it.